So now that we know how to find surface areas for parametrized surfaces, we can look at some special cases. And one of the valuable special cases we can look at is the case where our surface is the graph of a function of x and y. And in this activity, we're going to use that formulation as a way for us to reify the formula for the surface area of a sphere that we might have learned in high school geometry or whatever. And so the first question is, if our parameterization comes from the graph of a function of x and y, how does that give us a different perspective on the formula for surface area? So remember, for us, surface area is computed as the double integral of the magnitude of the cross product of the partial derivatives of our parameterization, right, over whatever appropriate range in parameter space, in ST space, that we need. So in the case where our surface is the graph of a function, graphs, because z is equal to f of x and y for a graph of the variables x and y, that comes with a built-in parameterization. We can just use s and t as replacements for x and y to give us a parameterization of the surface, which is a graph. And if I do that, then my parameterization looks like s, comma t, comma, and then the function, the same function f applied to s and t, right? So that gives us a built-in parameterization. And when I take that parameterization and I try to find the magnitude of the cross product of the partial derivatives, the partial derivatives are respectively 1, 0, and then the s partial of the function, and then 0, 1, and the t partial of the function. And when I take that cross product, what I get is the opposites. So minus the s partial derivative of f, minus the t partial derivative of f, and then the z coordinate of that of that cross product ends up being 1. We've actually seen this vector before. This was the vector that we saw back when we were finding equations for tangent planes to surfaces, which are the graph of a function. This is exactly the normal vector, a normal vector to the graph, normal vector to the tangent plane of the graph of f. And so to find surface area from that, we just need to take that vector, that normal vector, and find its magnitude, which gives us the square root of the sums of squares. And so what we get as a formula for surface area is just the double integral of the square root of the square of the s partial of f added to the square of the t partial plus 1, and then integrated ds dt. We could also have chosen to replace s and t with the x and y coordinates that they came from. Right? That's how we got our parameterization of a graph in the first place, is we just replaced x and y with s and t. And if I replace x and y with s and t, we'll get a formula that is the one that they sort of proffer in the book. So instead of s and t, we just remember that for a graph, s and t can mean the same thing as x and y. And so it's the square root of the x partial derivative of f squared added to the y partial derivative of f squared plus 1, and then integrated dx dy or dy dx, whichever is your favored approach for that. So what we'll do in this activity is use that approach, use the parameterization of a graph approach to come up with a formula for the surface area of a sphere of radius capital R. But before we do that, I want to rewind and look at how we might have done this with the ordinary parametric formulation, because we know how to parameterize a sphere using the spherical coordinate idea parameterization from the previous section. So how would I use the ordinary parameterization of a sphere to find surface area? Well, we've got to pull that parameterization off the shelf, right? We can parameterize a sphere by r sine s cosine t, r sine s sine t, and r cosine s, where r is the radius of my sphere, and s, the azimuthal angle, ranges from 0 to pi, so north pole to south pole, and t, the longitudinal angle, ranges from 0 to 2 pi, so from the prime meridian all the way around the globe back to the prime meridian again. So there's a parameterization for the sphere of radius capital R. If I want to find the surface area from this parameterization, I need to find the magnitude of the cross product of its partial derivatives. So we'll find its partial derivatives, take their cross product, and we get kind of a nasty looking cross product, right? R squared sine squared s cosine t, r squared sine squared s sine t, r squared sine s cosine s. But just like in our previous example, when we find the magnitude of that cross product, the Pythagorean identity comes riding in on a white horse. We use it twice to simplify the magnitude of this cross product significantly. So the magnitude is the square root of the sums of the squares of these. And so that square root starts out with a lot of junk underneath it. But what we notice is that the first two terms have a common factor of sine to the fourth of s that we factor out. And when I factor it out, the cofactors are cosine squared of t plus sine squared of t, which turns into a 1 by the Pythagorean identity, and leaving me with just sine to the fourth of s. But then that term and the last term, sine squared s cosine squared of s, also have a common factor. That common factor is sine squared of s, and its cofactor is sine squared s plus cosine squared s, which again turns into a 1. And so the only thing that survives underneath that square root is sine squared of s. And so its square root is just the absolute value of the sine of s. And so the magnitude of my cross product of partial derivatives is just r squared times the absolute value of the sine of s. And so that's going to be the thing that we're going to need to integrate over our ranges of s and t that are appropriate for my parametrization. Well, the good news about that absolute value is that because my s variable here ranges only from 0 to pi, the sine of s is always going to be non-negative over that interval. So even the absolute value here in this surface area integral ends up not mattering. We can just replace it with sine of s, because sine of s is non-negative, and so its absolute value is the same thing as itself for s's that range from 0 to pi. And so the surface area integral that we get is just r squared sine of s dt ds. And that integral, the integrand here doesn't depend on t at all. And so because of that, actually, that means that if we did this integral the opposite order, let's think of it like ds dt instead of dt ds. So I want to make another point right here about multiple integrals before we move on. Because this integrand, this function here, doesn't have any t's in it at all, in view of the t integral, so if I put some parentheses around the innermost integral here, so parentheses around my s integral, this whole quantity in the parentheses there is just a constant. It's not going to have a t in it, right? And because it doesn't have a t in it, when we integrate it with respect to t, it behaves just like a constant with respect to t. And anytime we have a constant inside of an integral, what can we do with it? We can just pull it outside of the integral. And so what I'm saying here is that this whole quantity in parentheses we can pull on the outside of my t integral. And if I pull it on the outside of my t integral, here's what it ends up looking like. Oops. I pull that on the outside of my t integral, and I end up with the integral with respect to s multiplied by the integral with respect to t. And then the integrand on that dt ends up just being a 1. Right? So this is a really happy incident here. This is an example of a case where an iterated integral ends up just being the same thing as a multiplication of two single variable integrals. Right? So we don't actually have to iterate at all. We can just decouple it. Right? And the reason that that happened was that my integrand didn't have a t in it. And so with respect to the t integral, it was just a constant. And so I can pull it out. And the same thing, by the way, happens anytime my integrand is a product of just a function of s and just a function of t, or just a function of x times just a function of y. And my integrals, my limits of integration, have constants as their bounds. Anytime those two conditions are satisfied, so the integrand is a product of two functions of a single variable and the limits of integration are all constant, instead of iterated integral, we can just make it into a product of two integrals. The s integral times the t integral, so that we don't have to do integration of integration. But whether we evaluate it as a product of integrals or whether we evaluate it as an iterated integral, we end up with 4 pi r squared as the answer, right? 2 pi coming from the t integral, from 0 to 2 pi of 1, and then r squared times a 2 coming from, whoops, this is a typo, sorry, this s integral goes from 0 to pi, not 0 to 2 pi. Where's my s integral? Sorry, let me fix that for the record. There we go. The integral of sine of s from 0 to 2 pi is equal to 2. And so we get a 2r squared from the s integral. We get a 2 pi from the t integral. Multiply those together, we get 4 pi r squared, which in high school geometry is our formula for the surface area of a sphere. So I wanted to present that both to kind of recap the process of computing surface area from a parametrization, and also to give us this little sort of happy accident of what happens when we're integrating a function of x times a function of y. So we can write the integrand as a product of two functions, each of which has only one of the variables in it. And when my limits of integration are constants, then instead of an iterated integral, we can just turn it into a product of two integrals. And you can do it with either approach. But the product of two integrals approach is sometimes just a little bit easier, so that you don't have to keep sort of, what's my constant, what's my variable. You don't have to keep those things straight. You can just evaluate them as single variable integrals and multiply the results. So now that we have seen the parameterization approach, this last problem is going to just have us use a graph approach to the evaluation of the surface area of a sphere. And so to do that, because a sphere doesn't pass the vertical line test, we're not going to be able to express the whole sphere as the graph of a function. And so the job is going to be to take the equation of a sphere in 3 dimensions, x squared plus y squared plus z squared equals r squared, and solve it for z, and then decide which portion of the sphere that you get as that solution, and then use that as our function f of x to use this surface area of a graph approach to find the surface area of that piece of sphere.